talk.
Recording in progress.
And I have explained that the aim of this talk yesterday. So the aim is I want to give the conceptual explanation of the type of this theorem for some convergence family of complex structure on symplectic manifold, such that the existence of one parameter family of JS such that the holomorphic sections of prequantum line bundle converging to the Dirac delta sections supported on every Bohr-Sommerfeld fiber. Then this is the outline. So from now on, I want to show that this is the space of holomorphic section, and I will show that this space is some of the eigenspace of some Riemannian metric G hat S. G hat S is the metric on S. S is a unit circle bundle of prequantum line bundle. Then I show that the convergence of this metric measure space with respect to measured Gromov-Hausdorff convergence, and there exists some limit metric measure space, and show the spectral convergence of delta G hat S. This is an Laplacian Laplace-Beltrami operator of G hat S as S to 0, and I want to study its limit. So today, first of all, I would like to explain the identification between this space of section and some eigenspace of some Riemannian matrix. I want to explain the relation between holomorphic sections and eigenfunctions on some Riemannian manifolds. Let X and omega be a symplectic manifold of dimension 2n. And I suppose that this is closed manifold, closed symplectic manifold. And let F and H and nabla be a prequantum line bundle. So nabla is a connection such that whose curvature form is equal to minus root minus 1 omega. Let J be an omega compatible complex structure X. Here, omega compatible means it satisfies this equation and the symmetric tensor defined by this is positive definite. And we put Gj this symmetric tensor. So Gj is given by omega and j like this. This is Riemannian metric on X. In particular, since J is omega compatible, so omega is scalar, and Gj is scalar metric on X. And we fix a positive integer k, and put Lk be the put Lk the tensor power of L. Then we put S or S LH. This is a subset of L. Absolute value is 1. This is a subset of L. So this is unit circle band of L. Then if in this case, if for any element U and for any element in S1, here S1 is the subset of complex numbers whose absolute value is 1. For any U and lambda, we can see U times lambda is also in S. So S is closed under the S1 action. And we can regard S as so let pi be the projection map associated with L. Then we restrict it to S. And then S is a principal S1 bundle on X. Then this is the frame bundle of L. So we may write Lk as this S times log kc. And this is an associated bundle S. Here, log k is one-dimensional representation of S1 given by lambda 2, so sorry, C star, lambda 2 k. This is a one-dimensional representation of S1. And I'd like to explain this set. This is the quotient space of S times C divided by some equivalence relation, the action of S1. Here, S1 on S times C is given by this. Let U and Xi be the element of an element of S times C. So U is in S, Xi in C, and let lambda be in S1. Then we define the action by U lambda and lambda 2 minus k xi. And we take the quotient space by this action. So we write the equivalence class by U times log k xi. This is an equivalence class of represented by U xi. So we can write Lk as this. Then we have the identification with the smooth sections of LK and the invariant space of C infinity S tensor C. We have this identification here. The right hand side means this is a subset of complex valued smooth functions on S. And this is smooth, and which satisfies if u lambda equal lambda minus k fu for any u and any lambda. So in other words, this is an invariant subspace by this action lambda star f times lambda to k. Here R lambda means the right action of lambda. Diffeomorphism given by the right action of lambda. Lambda is diffeomorphism between S given by U maps to U lambda. So this identification is given by, this is standard. So if we take F, then the corresponding smooth section of K is given by X maps to U times log K Fu, where U is in the fiber of X. So then you can see that this is in LKX, and this is independent of the choice of U. So we have this natural identification. Next, we have the operator on gamma LK. This is the operator. So now we have a connection nabla on L. Nabla is S1 connection on L. Then it induces naturally the connection on LK. And then nabla K d bar J is dz bar I tensor nabla d dz I bar. And Z1 to Zn is holomorphic coordinate on xj. Then I denote by delta dj bar k d bar Laplacian, which is defined by the formal adjoint of d bar operator and times d bar operator this linear map from gamma LK to gamma LK. So this is formula generated of the operator. Then, since I have assumed that X is closed, compact manifold without boundary, so the space of from exception of LJK, and this is the kernel of nabla dj bar k, is equal to kernel of d bar Laplacian. So this is because this direction of inclusion is obvious. This is easy. And the opposite direction, if phi is in kernel of d, then the else inner product of phi and d bar Laplacian of phi is given by d bar operator phi, the absolute value of d bar operator of phi and take square. And since this is 0, so nabla d bar j phi is 0. So this vector space is what we want to study, and it can be regarded as the kernel of some operator on gamma LK. Next, we consider the Riemannian metric on S given by GJ and the connection. Now, nabla is Hermitian connection, is the Hermitian connection equipped with L. Then we have connection form denoted by √-1a on S. And this is connection form corresponding to nabla. Since nabla preserves the Hermitian metric, so the corresponding connection form is S1 connection. So it is pure imaginary valued one form. Yeah, connection form means that the one form satisfying the pullback of R lambda is A, and A Gzi sharp is Gzi. Here, Gzi sharp means the vector field on S generated by S function. So defined by this. Gzi is an element of the real algebra of S1. And the shape is the vector field given by the action. Then, the tangent space of S has natural decomposition into horizontal subspace HU and vertical subspace VU. And HU is given by the kernel of AU. And VU is the tangent space of the fiber of the principal one. So we can decompose the tangent space into the fiber-wise tangent space and the tangent space along the fiber and the horizontal space. Then we define Riemannian metric. Define a Riemannian metric G hat J on S. The next matrix Gj 0, 0, A tensor A. And this decomposition is the decomposition of tangent space. So on the horizontal subspace, we use the metric on the base space X, and on the fiber, use the connection. And we suppose that this decomposition is also so we take G hat J such that this decomposition become orthogonal. Then we obtain Riemann metric on S, and we that the Riemannian manifold S with G hat J has S function, and this one action is the action of principal S1 bundle, and this action is isometric action. It preserves the metric. Then we obtain the Riemannian metric. Then we have the Laplace-Beltrami operator delta G hat J. This is this study, which is acting on the smooth functions on C infinity S. And we extend it C linearly. Now, since S1 acts isometrically, then this operator preserves the invariant subspace. So we have the operator denoted by delta G hat J log K, which is the restriction of this Laplacian to the invariant subspace. Moreover, recall that we have Laplacian on acting on the smooth sections of LK. This is Laplacian. And we have natural identification between these spaces. then we can compare these two operators. And it is known that 2 times d bar Laplacian acting on Lk is the Laplacian delta g hat j log k minus constant k square plus kn under the above identification. So this equal is based on this. This equal is based on this identification. So we can see that this is the space of holomorphic section of Lk, and it is equal to the kernel of d bar Laplacian, as I said. And moreover, by above proposition, this is identified with the eigenfunctions associated with the k squared plus kn eigenvalue. Of delta g j hat k. So what we want to do is that to analyze convergence of the holomorphic sections of LJK. And it is equivalent to analyze the convergence of eigenfunctions k square plus kn eigenspace of g hat j s. Sorry, JS is some family of one parameter family of omega compatible complex structure.
Sorry, there's a question in the chat.
Okay.
Which asks, could you perhaps say a couple of words of what goes into the proof?
Sorry, pardon?
Could you say a couple of words of what goes into the proof? That's the
proof. Which of proof? Which proof?
Yeah.
Sorry. A proposition, or this proposition.
Yes.
So, sorry. So to prove it, you decompose. We can decompose. So g hat j is given by this form, gj, and this form. So we will have to compute the Laplacian of g hat j directly. Then you can give the relation between this Laplacian and the connection Laplacian given by Nabla. Nabla is the connection on L. So you can compute the you can give the relation between this Laplacian and the connection Laplacian, and the difference is become constant. And then we can compute this connection Laplacian and d bar Laplacian. And this is, I think, the standard argument of complex geometry. holomorphic vector bundle. This is a rough sketch of the proof.
Okay, thank you. I guess that was
Okay. So now, yes, in the yesterday's talk, I received the question that we consider the convergence family of almost complex, integrable complex structure converging to some Lagrangian five bundle mu, and this convergence is the sense of polarization. And I said that this convergence contains more delicate conditions, and so from now on, I would like to explain the more precise condition for this convergence. And I call it the family of J's asymptotically semi-flat family. Now, let mu be Lagrangian fibration, and for the simplicity, we suppose that this is Lagrangian torus fibration. And X omega is compact, closed simple manifold. Then we take action angle coordinate on X. Let U be sufficiently small open neighborhood on B such that the restriction of omega to mu inverse U is given by dxi which d theta. So x1, xn, theta 1, theta n is the action angle coordinate. And x1 to xn is a coordinate on U. And theta 1 to theta n is the coordinate on every fiber. Then we describe the complex structure J by using these coordinates. By action angle coordinate. Now, we suppose that J is close to mu in the sense of polarization. Then, since J and mu is close to each other as a polarization, then the subbundle of 0, 1 anti-holomorphic tangent vector and the kernel of d mu is closed. So if we take the projection, here we have the decomposition of tangent space, tangent bundle, as the fiber was tangent space plus ddx, the direction of the action coordinate. So this this decomposition may depend on the choice of action angle coordinate, but we have direct decomposition of tangent space. So this is kernel d mu. So we have the projection map, and since if we suppose J is close to mu, then these two subbundles are close to each other. So this projection becomes surjective. So since this is surjective, we can take a basis. Basis of frame of TJ01X written as sigma j dd theta I plus aij bar ddxj. And this is frame of 01 vectors, local frame. And here, aij is a function on x and theta, and I and j moves from 1 to n. So this is matrix n times n matrix, and this corresponds to the local description of complex structure J. Then we can check J is omega compatible complex structure. So almost, I asked almost complex structure if only if aij is symmetric matrix and the imaginary part of aij is positive definite.
Excuse me?
Yes.
Do you want this vector del by del theta I in front of the sum or inside?
Sorry, pardon.
Yeah, well, in the sum, the first sum, you really want that n times?
This sum?
The sum, yeah. There is a d by d theta I plus
Yes.
j. So I just wonder if the d by d theta I should be repeated in each summand. Or do you want to have it?
Okay. So, sorry. I have mistake. Sorry.
Yeah, sorry, thanks.
Sorry, okay. I have mistake. So I think this should be, sorry. Sorry, this is correct. So sorry, I have mistaken. Okay. So I moves 1 to n. Then, so J is omega compatible most complex structure if aij is symmetric matrix and the imaginary part is positive definite. And moreover, if J is the integrability component of J is equivalent to some partial differential equation of Aij, but I omit it because I don't use it in this context. Now I define the asymptotically semi-flat family. Let JS be the one-parameter family of omega-compatible complex structure. Then it is called asymptotically semi-flat family. There exists a covering, open covering of B such that on every U alpha, on every mu inverse alpha, U alpha, there exists action angle coordinate. So x1, xn, and theta 1, theta n is action angle coordinate. On mu inverse U alpha. And the next conditions hold. The first one is Aij S x theta. So this is a local description of JS. So this is the local description of JS on U alpha. And Aij Sx theta is C infinity in S and X and theta. Maybe this condition can be weakened, but for the simplicity, I suppose these are C infinity. And we suppose Aij 0 x theta is 0. So sorry, S now S is defined on positive, but it can be extended to 0, smoothly extended to 0, and so we suppose that Aij is C infinity in S on the neighborhood of S equals 0. And we suppose the imaginary part of Aij Sx theta is given by this expansion of S times Qijx plus the higher order of S. And we suppose the matrix Qij is positive definite. This is assumption. So I think the first two conditions, these two conditions is natural because we suppose that for as S0 JS converges to mu, so if Aij, if S equals 0, then this corresponds to the polarization, real polarization given by mu. So this is natural condition. And the third condition, this condition means that, so if this is C infinity in S, so we can extend to by S, and the coefficient of S20 is 0 because of the second condition. And then this is the coefficient of linear term. And in general, this should become Qij x theta, but I suppose that this is independent of theta. This is assumption. And moreover, by the assumption of Aij, we can see that so Aij is supposed to be its imaginary part of positive definite. So by taking s to 0, then we can show that Qij is semi-positive definite, but I assume it is positive. This is the second assumption. So the third condition contains two assumptions. This condition contains two assumptions. One is that Qij x theta is independent of theta. This is first assumption. And the second assumption is Qij is positive definite. So we always, in this talk, we always consider this family. Then next, I want to explain the spectral convergence results on Riemannian manifolds. Now let xi, gi be a closed Riemannian manifold of whose dimension is n, and n is independent of I, and I is positive integer or a positive integer. So this is a sequence of closed Riemannian manifold of same dimension. And I denote by dgi the Riemannian distance of gi, and mu gi is the Riemannian measure. So by the local coordinate, by using local coordinate, this is given by square root of determinant of d gij times dx1 dxn. And we denote by delta gi the Laplace operator, Laplace Bertrand operator. Then there are several types of spectral convergence theorem. Here, I'd like to explain the spectral convergence result in rough statement. I will explain the precise statement in the tomorrow's session. And these type of spectral convergence results are shown by Kenji Fukaya and Shiga and Colding, and so on. So, and I will also mention the spectral convergence result by Kuai and Shioya. So Fukaya and Chiga Colding's result is the spectral convergence for compact Riemannian manifolds, and Shioya's result is for the sequence of Riemannian manifolds, which may include the non-compact Riemann manifold. The spectral convergence means that we assume the metric measure space given by GI converges as I to infinity to some metric measure space x infinity, d infinity, mu infinity. Here, the sequence, this sequence comes from Riemannian manifold, smooth Riemannian manifold, but the limit space may have singular. This is not manifold. And this convergence is in the sense of measured Gromov-Hausdorff topology. Then, moreover, we need some assumption for the bound of the geometric constants on xi. Then this is assumption. Then the conclusion is the spectral convergence of on xi. Here we consider the pair of Hilbert space and the Laplacian. Then it converges to the Hilbert space on the limit space with the Laplacian on the limit space. So I said that the limit space is not manifold, not manifold, but it is known that if the limit space is the measured Gromov-Hausdorff limit of some Riemannian manifolds with some assumptions, then the limit has the Laplace operator, which is a generalization of the Laplacian on Riemannian manifold. So we get the Laplacian on the limit space. Then we have the convergence of the Laplacian. This is the spectral convergence. And so I have to say what is the topology of. Now I have to explain two types of topology. One is measured Gromov-Hausdorff topology, and the other is the convergence of Laplacian. So the second one, this spectral convergence I will explain this spectral convergence on the tomorrow's session, and maybe I can explain the first one. So okay. So I explain the measured Gromov-Hausdorff topology. Let xi di mu I be a metric measure space and I is in integer or infinity. Here xi di mu I may be not manifold, but metric measure space. And maybe we need some compatibility of di and mu I. So I think it is enough that mu I is random measure, and so mu I is defined on the Borel sets of the topology on xi. Then we can define the convergence of the metric measure space. We write it MGH topology. If the next condition holds, there exists a positive real number epsilon I tending to 0, and there exists a map phi I from xi to x infinity. This is Borel map, but I don't assume the continuity of phi I, but assume Borel map such that the first condition is the difference between d infinity phi I x phi I y minus di xy is less than epsilon I. And x infinity is included in the epsilon neighborhood of image of phi I. And the third condition is the convergence of measure. Integral xi, the composition of f and phi I, and integrate by mu I, then it converges to the integration on x infinity of f for any continuous function with compact support. These are the conditions. If there exists such phi I and epsilon I, then we said that this metric measure space converges to the limit in the sense of measured Gromov-Hausdorff topology. So this is this may be very difficult definition. So I will explain the typical example of the Gromov-Hausdorff convergence in the exercise session in this afternoon. So let me explain one more definition, and I finish the second talk. Then next, I consider the sequence of pointed metric measure space. So Pi is the point in xi, and P infinity is the point in x infinity. Then this sequence converges with respect to pointed measured Gromov-Hausdorff topology if the next condition holds. There exists some positive real number epsilon I tending to 0, and there exists positive number Ri and Ri prime tending to infinity, and there exists phi I, map phi I. This is also Borel map, and the domain is the open ball of radius Ri prime centered at Pi to x infinity, such that phi I maps Pi to P infinity, and so the I number this condition 1 and this condition 2. So we suppose and 1 and 2 is satisfied, and for we need this condition in the case of pointed case. It is given by the open ball centered at P infinity, whose radius is Ri minus epsilon I, is contained in B, the open ball epsilon neighborhood of the image of phi I. If this condition holds, then we we say that this pointed metric measure spaces converges. So let me explain two examples. If xi and di and pi is xi is some set like this cylindrical set, and let di be the distance on x, and such that the width of here is 2 minus I, and let pi be the base point located on here. Then this metric space, now I explain the convergence of metric, pointed metric space. Then this, if we take I to infinity, then this metric space converges with respect to pointed metric space to this line, half line, and the base point is here. This is the limit space. And if we take pi prime, here, and the distance between pi and pi prime is 2 to I, so it diverges. If it diverges, then in this case, x with di and pi prime converges to the space, not half line, the line with the base point is here. This is an intuitive example of pointed the convergence of pointed metric space. So it's time to stop. So okay, I stop here. Yeah, sorry, and I will in the afternoon session I have one exercise session. So I will explain the more elementary one elementary example of the Gromov-Hausdorff converging sequence, and how to show the I want to explain how to show the Gromov-Hausdorff convergence. Okay, I stop here. Thank you.
Okay, thank you very much. Let's. Right. Are there any questions about the talk, either here or online? Doesn't seem to be the case right now, but yeah, this afternoon there's an exercise session. So any questions that come there? So let's thank the speaker again.
Thank you.